everyone! Today we are going to be talking about eddy fluxes. In class on Thursday, we discussed diffusive fluxes and Brownian motion, and at the end of class I introduced eddy diffusivity and eddy flux, which can be parameterized in a similar way to diffusive fluxes. We will be using an example from the Gulf Stream where eddies break off from the core of the warm and salty Gulf Stream and cause horizontal fluxes of temperature, salinity, and other biogeochemical properties onto the continental shelf. These filaments are smaller scale and more variable than the mean flow, and again, we can describe them in a similar form to diffusive fluxes, which we talked about in class on Thursday. Okay, so as I mentioned, we are going to be looking at an example of cross-shelf transport of heat by Gulf Stream eddies. We are using heat as a tracer for this example. Salinity would also work for the Gulf Stream or other biogeochemical properties that are transported horizontally across the shelf break. So here we have the shelf break. Just imagine somewhere off of Rhode Island or Cape Cod area. We observe the core or the mean flow of the warm, salty Gulf Stream moving waters northward, just offshore of the shelf break. The mean flow does not cross onto the shelf, but small filaments or eddies break off from the core of the Gulf Stream and cross onto the continental shelf. At the same time, cool shelf waters move offshore, transporting waters off the continental shelf. Now, if we placed a mooring on the shelf break, we could measure fluxes across the shelf break as a function of time. This would provide us with an Eulerian time series of cross-shelf current or velocity and temperature. So imagine we measure velocity and temperature from a mooring such as before, and we plot as a function of time. The time series might look something like this. When transport is onto the shelf, horizontal velocities are positive, and when transport is offshore or off of the shelf, horizontal velocities are negative. Same idea with temperature. When warm filaments from the Gulf Stream cross over onto the shelf, the temperature is warmer. Vice versa, colder when cool shelf waters move offshore. We can define a mean velocity and mean temperature of each time series. The over bar on each simply means average or mean. In both cases, let's just suppose that our mean velocity and mean temperature are both positive. Now we can describe how velocity and temperature change as a function of time. This is simply the mean added to the time-varying anomaly. The anomaly is simply the deviation from the mean, and we'll denote it by u prime of t and big T temperature prime of t. So every data point can be described as the mean plus the deviation from the mean. If we think about what the plot of the time-varying anomaly would look like for both velocity and temperature, it would have the same shape as the two plots above. However, it would be shifted up or down by the mean, and therefore centered around 0. So, if you take the average of each of the time-varying anomalies, it will always be 0. If this idea doesn't click for you, and it didn't for me the first time I learned this stuff, I suggest making up 5 or 6 arbitrary points and finding the average. Then you can subtract the average away from each of the points to calculate the anomaly. The average of the anomaly will always be 0. Okay, with this idea in mind, we can calculate the temperature flux on or off the shelf as the velocity u times the temperature T. We substitute into our equations from before and distribute to get u bar t bar plus u bar t prime plus u prime t bar plus u prime t T prime. If we take the time average to determine temperature flux, we can eliminate two terms in our equation. The average of u bar times t prime is equal to 0 because the average velocity, u bar, is simply a constant and not time dependent. And the average of the temperature anomaly is 0, as we previously discussed. The same reasoning applies to the third term. The average of u prime times t bar is equal to 0. Now we are simply left with this equation for mean temperature flux. We have our first term, which is our mean flux of temperature, and the second term, which is our eddy flux. Now you might be wondering why I've kept this eddy flux term in the equation. If the time average of u prime and t prime both have to equal 0, then they should still be 0 if multiplied together, and then time averaged. This, however, is not the case, and our eddy flux term does not have to equal 0. I will explain with the following simple example. Imagine our first anomaly can be described by the sine function. Simple sine curve, and as always, the average is 0. Let's say our second anomaly can also be described by the sine function. Our plotted anomaly as a function of time looks the same as before, and the average is again 0. Now, if we multiply these anomalies together, we see that our time series looks very different, because when we multiply two negatives, we get a positive. Now when we take the time average, it does not equal 0. We'll use the same approach for our Gulf Stream example. If we plot the anomalies from the time series, we might have something that looks like this. Both are averaged around 0. However, if we multiply the anomalies and plot u prime times t prime, we see that the average is not 0, and we get a net transport of eddy-driven heat flux onto the shelf in this example. So again, this is kind of what our horizontal transport looks like from the Gulf Stream onto the continental shelf. We have eddies and filaments that transport heat onto the shelf, and warm fluxes occur when waters move onshore. It makes sense that anomalies u prime and t prime are correlated because with onshore transport we observe warm waters in the Gulf Stream. We observe warm waters of the Gulf Stream move onto the shelf to allow cool shelf waters to move offshore and replace the displaced filament. We'll look at this a bit more closely as a real-world example. Here is a video of sea surface temperature in the Gulf Stream region with arrows denoting velocity. We observe this eddy developing right in the middle of the screen, bringing warm waters into the middle of the basin. We'll do the same analysis, but this time we'll look at fluxes across the span of the eddy, so rather than looking at velocity and temperature as a function of time, we'll study them as a function of x. Okay, so I'm going to switch back to notes again. Here is the eddy we were just looking at, and we're trying to determine the temperature flux across the span of the eddy. So we'll measure velocity in the y direction, or v, and temperature T across the line. Our equation for velocity as a function of x is the same as before, except now we're measuring velocity in the y direction, so we are using v. So we have v is equal to the average velocity plus v prime of x, which this time is the spatial varying anomaly. Our plot of velocity might look something like this. We have the strongest velocities in the ring of the eddy, but in opposite directions. In the middle, we have little to no velocity. Let's just say we measure velocities between negative 0.1 and 0.1. In this case, our average velocity is approximately 0, so our anomaly and our velocity looks just about the same, varying between negative 0.1 and 0.1. Now we'll look at temperature in the same way, as a function of x. Our equation is the same as above, so we can find T of x by adding the average temperature to the spatial varying anomaly. There is no color bar, so we'll have to approximate our temperature, but the curve will look something like this. We will have warmer waters from the Gulf Stream on the left-hand side of the eddy, and then they decrease as we move spatially in x before increasing on the right-hand side of the eddy again. Let's just say our temperature is ranging between 22 and 24 degrees C. This means our average temperature is probably somewhere around 23 degrees Celsius. In this case, our spatial varying anomaly will look something like this, with the same curve as above, but now we vary between negative 1 and 1. As always, the average of the spatial anomaly is 0. Now, if we multiply the velocity anomaly and the temperature anomaly, our curve will look something like this. Notice the flux is always negative, meaning that our average temperature flux is always in the negative y direction, or away from the Gulf Stream. If we find the average eddy flux, it will probably be somewhere around negative 0.03 centimeters per second. But again, most importantly, the average eddy flux is not 0 and has a negative value, meaning that warm waters are fluxed in the negative y direction or away from the core of the Gulf Stream. Alright, so I'll play this video again for you guys to observe some of other eddies and filaments breaking away from the Gulf Stream. And I think that's all I have for you today. So we will see you in class on Thursday.